You may be familiar with the fact that as an ice skater pulls their arms and legs in closer to their body, they start spinning faster and faster and faster. But do you know why that's the case, or how to describe it? What's the physics behind this phenomenon? Well, it has to do with conservation of momentum. So let's do a quick review, a little bit about conservation of momentum. We had these two carts on a track, and the total momentum before they collide should equal the total momentum after they collide. So if they collide and stick together, if they had 3 times as much mass, they should have 1/3 as much velocity. And we called this linear momentum, although we didn't actually clarify before. We didn't know there was different kinds of momentum. In this example, the total momentum before was 0, so after we explode them apart, the total momentum should also be 0. This car was going to the left with about 3 times the velocity as this car was going to the right, because this one had about 3 times as much mass. Momentum to the left was negative and momentum to the right was positive. And here, these two cars bounce elastically. They just swapped momentums. All right, so instead of doing momentum on a track where things move in a line, or on an air table where things move in a plane, let's consider momentum on a turntable here with a bicycle seat. So we're not going to be talking about conservation of linear momentum. We're going to be talking about conservation of angular momentum, things rotating through angles, where we used the letter P to abbreviate momentum. And that's because it is based on the Latin word patere, or as I like to say, potentum. You see what I did there? Momentum, potentum? All right. Likewise, we're going to have a different letter for angular momentum. And the letter we use is the letter L, a capital L. And there doesn't seem to be good reason why we use L, but we do. Maybe it stands for langular lolentum, angular momentum. All right. So we're going to look at conservation of angular momentum, where the total angular momentum initially should equal the total angular momentum finally. And I'm not going to define angular momentum just yet. I will in a little bit, but let's just rely on our intuition about what it might mean. So for example, here I am sitting on this turntable, and I'm holding a bicycle wheel. The wheel is stopped, and I am stopped, so the total angular momentum right now is 0. What's the total angular momentum right now going to be? Everything's moving, but the two things are moving in opposite directions. So if the wheel was initially going counterclockwise, the wheel was initially stopped, but now that it's spinning, it's going counterclockwise, so it's positive momentum. I started spinning clockwise, so I get negative momentum, but the total momentum before was 0, and the total momentum after is going to be 0. All right, let's do this example. The wheel is already rotating. It has a bunch of angular momentum in the counterclockwise direction. I'm going to grab and stop this wheel from spinning while I'm sitting on this turntable. So I'm going to grab and stop it, and you can see that I started spinning in the same direction the wheel was initially spinning. So the wheel initially had positive angular momentum. It was going counterclockwise, and I was stopped. The total momentum before was positive 1. So afterwards, the wheel was stopped, and I began moving in that same direction. Total before equals the total after. All right, just that I had 0, the wheel got 0, the wheel had 1, I got 1. All right, now this is a little more complicated example because we have to look at the initial angular momentum in a particular direction. So right now, the wheel is spinning with angular momentum in the counterclockwise direction, but it is in the plane of the floor. Okay, it's moving horizontal. And then I'm going to take and I'm going to turn this wheel. I'm going to rotate the wheel up like this. Well, right now, if I do that, the wheel doesn't have any angular momentum in the plane of the floor. So where did that angular momentum go? It gets transferred to me. And then if I rotate the wheel back, I can transfer it back to the wheel. Here we go. I rotate it. I get the angular momentum, I rotate it back, I give it back to the wheel. But the total angular momentum in the plane of the floor remained the same before and after. So initially it was +1 and I was 0, total of 1. Rotating it a quarter of a turn, I stopped it from going in that plane. Now it did have momentum in a different plane, but we're just looking at the plane of the floor right now. And then I got the momentum, but the total momentum the whole time was +1. And this is after I flipped it back to the original position. So there, and there. All right. This is a lot more complicated problem because I'm not going to just rotate it a quarter of a turn like this. I'm going to keep rotating it another quarter of a turn or a full half turn. You can see that the wheel has started rotating in the complete opposite direction than it initially was. I want you to predict what's going to happen to me when I rotate it all the way around. I really want you to hit pause here. Don't deprive your brain of an opportunity to think about difficult problems. Okay, so you hit pause. I hope you did. But here we go. Right there is a quarter of a turn, and right there is a full turn. Makes me sick just looking at that. But the total angular momentum was the same all throughout that thing in the plane of the floor. Here's what happened. Initially, the wheel was spinning with a +1 counterclockwise, and I was stopped. And this was the previous example where I stopped it from rotating in the plane of the floor. But when I rotate it another quarter of a turn, the wheel is now rotating in the opposite direction than it initially was. So when it has negative momentum now, I need that much more positive momentum to have the same total momentum as it was throughout. And then when I rotated it back to where it finally was, that's where it was. We probably should see that again. Okay, so there is just quarter turn, and there's all the way around. Wow. All right. So in this example, the wheel is starting in the vertical direction. It has no momentum in the horizontal plane, parallel to the floor. If I rotate it this way, I have added some counterclockwise momentum where previously it did not. So I'm going to get clockwise momentum to keep the total momentum 0. If I rotate it the other direction, now this has clockwise rotation, I would need an equal amount of counterclockwise rotation to keep the total momentum the same before and after. So here we go. Rotate one way, I go that. Rotate the other way, I do that. All right, so that just gives you some ideas of conservation of angular momentum. How would we apply that? Well, let's say you're jumping on a motocross bike here, and you're coming in at way too steep of an angle that when you hit the ground, you're going to flip onto your back and crash, roll, flip, and burn. We don't want to do that. So we do have a nice thing here is that when we were racing off the ramp, these wheels were rotating in this direction. So I need to rotate clockwise. Should I hit the brakes or should I give it gas? Maybe hit pause here again. Well, we're back. Let's see what happens if we hit the brakes. If we stop these wheels from rotating, the momentum doesn't just evaporate, it is conserved. That momentum gets transferred to the whole bike, and the whole bike will begin to rotate like this. If you're coming in at too steep of an angle, and this wheel was spinning like this, we could get that wheel spinning faster, give that wheel more momentum in the clockwise direction, and the whole bike would respond by moving in the counterclockwise direction, so that these two added together after is the same as what it was before. And the James Webb Space Telescope, how do you get this up in space and then now point it in different directions? Well, it is really just taking little bicycle wheels, really fancy, very expensive bicycle wheels, and getting them spinning faster or slower or rotating them in different directions. The total angular momentum of that would allow it to rotate and look at different stars. All right, so let's now think about the definition of angular momentum. And we're going to rely on our idea of what momentum was. It was inertia in motion. With linear momentum, we could just plug in how much mass it had and multiply by how fast it was going. But if something's rotating, we learned in the last video that we have to consider more than just how much mass it has. We have to consider its rotational inertia. That would be like how that mass is distributed and what the size of its radius is. Okay, so we had equations to calculate how much rotational inertia the variety of different shapes had. And it's not going to be a velocity, it's going to be an angular velocity, something rotating. But it's still inertia in motion. We just have to be a little bit more careful. We can't just plug in the mass, and we can't just plug in its linear velocity. We have to calculate how much inertia it has and how fast it's going angularly. One thing you might notice here is that I do not have arrows over the top of these two things. I'm not treating this as a vector. I am going to do that in my next video, but right now we're just looking at the magnitude of these things, not the direction. Okay, so here I'm sitting back on this turntable with bicycle seat, and I'm holding 8-pound weights in each hand. And I am spinning around like this, and I pull my arms in, and I spin a whole lot faster. Put my arms out, I spin slower. But angular momentum was conserved. So when I pull my arms in, which quantity decreases? Well, it's going to be rotational inertia. You get that mass closer to the axis of rotation, it has less rotational inertia. Which quantity increased? Well, I started spinning faster angularly, so the angular velocity increased. And then which quantity remained the same? Well, momentum was conserved, so the total momentum before was equal to the total momentum finally, or afterwards. One thing important to understand here is that because I have rotational inertia and angular velocity equaling rotational inertia and angular velocity, we really do not need to be that careful with our units. Because if I measure angular velocity in, say, revolutions per hour, and then this would also be measured in revolutions per hour. Okay, because it would be the same on both sides. If I do some funny units for this and some funny units for that, because the units are on the same, on opposite sides of the equation, those units will cancel. So if I have an ice skater in this position here, and they change from this position to this position, the angular momentum is going to be conserved. That here their mass is as far from that axis as they can get it, so a lot of rotational inertia and a little bit of angular velocity. Here their mass is as close to that axis as you can get it, so a little bit of rotational inertia and a lot of angular velocity. Okay. And then let's say we have these two space pods tethered by a cable, and they're rotating at 4 revolutions per minute. Now those are not MKS units, but it will work because of this. Those units are going to be on either side of the equation. If I pulled those masses in, so they're now at 1/2 the radius that they originally were at, momentum is going to be conserved, but what will be the final angular velocity? Total momentum initially should equal the total momentum finally. There are 2 of them, so there's a pod here and a pod here, And so it's going to be twice the angular momentum of just one of them. We're saying they're identical. And the rotational inertia for just a mass spinning around in a circle like that, kind of like a simple pendulum, is just mass times radius squared. The initial angular velocity was 4, and everything else here is the same except it had half the radius. So same thing here, I'm going to take that and square it, so the half becomes 1/4. The radius gets squared and gets radius squared. There's a 2 in both sides, there's a mass in both sides, and there's a radius squared in both sides. So if I multiply both sides by 4, the angular velocity will be 16 revolutions per minute. Whatever the units of this one initially were, the units of this will also be the same. So it will be spinning a lot faster. All right. Angular momentum is always going to be conserved, okay? Unless it is acted upon by an outside torque. Torque can change the angular momentum. But not all forces produce torques. If I put a force right through the pivot point of this bicycle wheel, it's going to change its linear momentum, but it wouldn't have changed its angular momentum. I have to put a force at some distance to the pivot point to change its angular momentum. And it's a good thing that you can do this, because if this helicopter were parked on the helipad there and the engine's turned off, nothing's spinning, and now you got in there and you turned the key and you started this up, if the blades started rotating in this direction, the whole helicopter would start rotating in the opposite direction to conserve angular momentum. We don't want that to happen. So that's what this little guy back here is for. It's blowing air out that way to put a force on it this way. And that force is acting at a distance, creating a torque that will allow the angular momentum of the system to increase. And then before we move on, I want to just remind you of a lab that we did earlier in the year when we talked about impulse with linear momentum. This cart collided into a spring which had a force sensor. And the force sensor peaked up like this as it compressed, as the cart compressed the spring, and then it dropped off like this as it sprung back. And at that same time, the cart was moving to the right and had some positive velocity, and then it bounced backwards with some negative velocity. What we wanted to do was to see if the change in momentum, which is mass times change in velocity, was the same as the impulse that was put onto it, the force times the time. And we did find that that was true. So an impulse causes a change in momentum. And in a linear sense, the change in momentum was mass times change in velocity, and we could calculate that with force times change in time. We found that an impulse of 200 Newton seconds, that's force and time, causes a change in momentum of 200 kilogram meters per second. That's a mass and a velocity. Now, in an angular sense, how do we have to adapt this? Well, it's not going to be just the mass, it's going to be its rotational inertia. And it's going to be not a linear velocity, but an angular velocity. Similarly, we can't just plug in how much force we put on it, because that force is going to have different effects depending on the distance that force is applied. So we have to calculate the torque, which was force times distance. So this is an angular impulse, a change in momentum. So if I have an angular impulse of 200 Newton meters seconds, causes a change in angular momentum of 200 kilogram meters squared per second. It's going to be the same units here, except with this torque and with this, we're going to get an extra unit of distance. We're going to get an extra unit of meters in both of these than we had here. All right, so here's an example. This wheel is going to be initially spinning at 24.1 radians per second. The wheel has a radius of 0.31 meters. It has a mass of 4.1 kilograms. And I'm going to push perpendicular to the surface here with a force, a normal force, of 4.9 newtons. When I do that, there's going to be some friction between my hand and the rim. And we can calculate how much friction there is by knowing the coefficient of friction. I want to find out how much time is it going to take this wheel to come to a stop, to change from that to zero. Okay, so this force is going to provide at this distance, providing this torque. All right, so change in angular momentum was the change in the rotational inertia, or the rotational inertia times the change in the angular velocity. That's the change in angular momentum, but we can also calculate that by an angular impulse. So this is a ring, so we're going to calculate it with mass times radius squared and change in angular velocity. So we know these terms. I should say here, the frictional force, this force here that was acting at this distance here, can be calculated by the coefficient of friction times the normal force. The radius squared on this side and radius cancels there, and I'm going to solve for the time. So I know the radius, I know the mass, I know the radius, I know the change in angular velocity, I know the coefficient of friction, I know the normal force. Looks like it's going to take 6 seconds for that to come to a stop. So here we go. Right there we touch it and it goes slower and slower and slower and slower, taking 6 seconds to come to a stop. All right, let's apply that here. We already looked at that angular momentum was not conserved because there was this torque provided back here. But let's say in addition to that, the engine is going to get this thing spinning faster and faster and faster. So my question is, I would like to know how much torque the engine must provide for the blades to accelerate from rest to 500 revolutions per minute in 30 seconds. Okay? And my question here is, what else must be known for me to find this? Well, the change in angular momentum should equal the angular impulse. And I know the change in angular velocity, although because I don't have angular velocity on this side and this side, I need to be careful with my units. So I did convert revolutions per minute into radians per second. Radians per second is our unit, is our MKS unit. Okay, my question is, I want to find the torque. I know the time. What else do I need to know? Well, I need to be able to calculate how much rotational inertia those blades have. And back when we introduced rotational inertia, we introduced the idea of a stick pivoting about its end, and the rotational inertia is 1/3 mass times length squared. So we need to know the mass of those blades, and we need to know the length of those blades. There are 4 of them, so the total here is going to be multiplied by 4. All right, let me introduce this next and last topic with this video here. Kid doing a zip line, going down, got momentum, and whoop. Okay. We're going to turn linear momentum into angular momentum. How does that work? So here the kid was moving down with some linear momentum, and then something happened to cause him to get some angular momentum. What do we do there? Well, we're going to take our equations that we've done for a long time now, converting an angular something into a tangential or a linear something. Momentum is just mass times velocity. Angular momentum is rotational inertia times angular velocity. So let's see if we can manipulate these things and get it into something like that. This is just a mass moving around, so it's going to be just like a simple pendulum or a ring even. So we're just going to take this and substitute it in for rotational inertia. We're taking this piece of it here and rearranging for the angular velocity. It's the tangential velocity divided by the radius. So one of the radius here will cancel out with the bottom, and I'm just left with mass times velocity times radius. Let me explain. Mass times velocity is momentum. So when that kid was going down with some momentum, that momentum was at some distance from the pivot point, which was the handles the kid was hanging on to. And that's how much angular momentum the kid had in potential. That if the handle stopped, this amount of linear momentum acting at this distance to pivot would be transformed into this angular momentum. Here's an example. Okay. Guy was going to jump up and over the railing, but his feet slipped and he ended up rotating around the railing. All right. If that railing were higher up here, and this is the person's center of mass, if their momentum hit right there, they would have just stopped and they wouldn't have rotated around there. But if that railing were lower and the pivot point shifted down like this, now their momentum is acting at some distance to a pivot point. This amount of linear momentum acting at this distance is going to be transformed into an equal amount of angular momentum. So the amount of angular momentum they had in potentiality, meaning they had the potential of turning into this, is going to equal what it finally was. So the amount of angular momentum they had initially was their momentum times that distance. And that was turned into rotational inertia and angular velocity. This person is like a stick pivoting in their middle, and the amount of rotational inertia is 1/12 mass times their length squared. So this is what we would do to solve the problem. I guess we would like to ask what the problem would be. Maybe we should say, hey, let's find what their angular velocity is going to be. Their mass cancels out, so if I knew how fast they were running and how much distance between the pivot point and their center of mass and the length of them, I could calculate their angular velocity. Lastly, we did not treat these as vector quantities. We treated angular momentum just by looking at the magnitude of it, but didn't really look at the direction in space. We're going to turn each of these in my next video. We're going to look at the vector nature of these two things. We had to, in this video, draw angular momentum as rotating around like this. But if it's a vector, I should be able to draw it as a straight arrow. So think about that as we get ready for our next video. But that is a little something about angular momentum, angular impulse, and turning linear momentum into angular momentum.